Hello everyone, I'm Mu Liang from Xidan University. In this video, I'm going to introduce our new work on novel class discovery in CVPR 2023. Novel class discovery aims to partition unlabeled data into several clusters according to semantic classes, using the knowledge learned from the labeled base data. Most existing works hold an impractical assumption that the unlabeled novel data is class-managed, which I think is hardly the case in the real world. In this paper, we propose a new setting, distribution-agnostic novel class discovery, the challenge of which lies in the dilemma that an accurate class prior is necessary yet is unknown. We propose to solve this dilemma by bootstrapping your own prior, which iteratively estimates the class distribution prior using a model prediction itself. The visualization shows that our method can produce more accurate cluster results under high data imbalance. Novel class discovery aims to cluster unlabeled data according to semantic classes, instead of colors or backgrounds. This is the inherent difference between NCD and unsupervised clustering. To this end, existing works often hold a common assumption that unlabeled data has a uniform class distribution. But why is the uniform class distribution a common assumption? The short answer is, this is a huge simplification of the problem such that we can focus more on how to transfer the knowledge from base data to novel data. For example, when ambiguity presents, one can rely on the uniform clustering prior according to this uniform class distribution assumption. However, the novel data can hardly be balanced in the real world. This case is related to the long-tailed learning problem if we have labels, and we can use the label distribution to easily debias, like reweighting or resampling. But in our case, we don't have labels. This is very much different from the supervised scenario. It actually gives rise to a chicken-egg problem. The class distribution prior is necessary to the accurate clustering results, but is unknown. So in this work, we relax the unrealistic uniform distribution assumption and study this new task termed distribution-agnostic NCD. Basically, we want to build a model that is able to effectively discover novel classes with any unknown arbitrary class distributions. We propose to solve this challenging problem by bootstrapping your own prior, which iteratively estimates the class distribution prior using the model prediction itself. Our proposed approach contains 3 steps. The first step is to cluster the unlabeled data using the current class prior, for which we employ an optimal transport-based clustering method. The basic idea is to regard the classifier weights as a set of cluster centers, and the clustering is to assign image features X to each cluster center. This assignment can be used as pseudo-labels Y to train a classifier for the novel data. Y is optimized by this term. The search space of Y, or the transportation polytope, is constrained by current class prior P, which will be updated in step 3, and the whole optimization problem can be solved by Sinkhorn-Knopp algorithm. The second step is to train a classifier using labels or pseudo-labels for base or novel data. Here we propose a dynamic temperature technique to encourage confident predictions, which helps more accurate prior estimation. The motivation is that the ambiguity in the pseudo-labels causes the ambiguous prediction for novel samples, which results in inaccurate prior estimation and again increases the ambiguity in the pseudo-labels. It's like a vicious cycle. So we propose to explicitly encourage more confident predictions for ambiguous samples. Since temperature parameter in the softmax controls the sharpness of the output distribution, we can use a larger temperature for ambiguous predictions to amplify the CE loss values for them, which in turn encourages more confident predictions. The third step is to estimate the class prior based on the model prediction, where we use a first-in, first-out queue to encourage more stable prior estimation. This design requires no extra computation and can fast adapt the class prior across iterations. At the very beginning, we initialize the class prior as the uniform distribution, and after that, we use this moving average manner to update it, which is more stable. We repeat these 3 steps for each iteration in training, which dynamically estimate the class prior for novel data and helps generate more accuracy to labels, resulting in better class prediction results. In experiments, each dataset is split into base subset and novel subset. Each subset is again split into training data and testing data. For distribution-agnostic NCD, training data is imbalanced, which is controlled by imbalance ratio, and testing data is balanced, following the non-tailed learning literature. We have 3 evaluation metrics to comprehensively evaluate the model, which are traditional protocol, task-aware protocol, and task-agnostic protocol. Here are the results of comparison with SOTAS. We have tested our model across different imbalance ratios with the 3 evaluation metrics. The improvements are most significant with the traditional protocol, which directly benefits from our method. Still, our method can also generalize to the balanced testing distribution, suggesting that our more accurate class prior also helps the feature learning. Other datasets can also see the similar improvement. Benefiting from the estimated class prior, we can leverage the sophisticated long-tail learning technique, which further improves our approach. We tested 2 major components for ablation study. As for the estimated prior, we compare it with the uniform prior and the oracle prior, and the results show that the estimated prior already has similar effect of the oracle prior. So adding the dynamic temperature further improves the performance. The improvements mostly come from the many shot samples, which can easily be misclustered under the uniform prior. I think this visualization can better explain the large improvement of the many shot samples. So with a uniform class prior, traditional method tends to output same-sized clusters that easily split the many shot samples into different clusters, but our method can alleviate such a problem, which better preserves the true data structure. This visualization shows the estimated prior versus the true prior. We can see that the discrepancy is already small. That's all of my sharing. Thank you for listening.